On this question, we want to construct a polynomial function that might have the given graph. So we're given this graph of a polynomial function, and we want to take a look at our zeros, our x-intercepts, because the zeros tell us what the factors of our polynomial will be. So because we have a 0 of -4, that means that our polynomial will have a factor of x plus 4. Here we have a 0 of -2. However, this particular 0 is touching the x-axis, and that means that it has a multiplicity of 2. So I know that instead of having just one factor of x plus 2, it's going to have two factors of x plus 2. And it might not have two factors, but we do know that it's going to have an even number of factors. So because the graph touches at that 0, we're going to have an even number of factors instead of an odd number of factors. This x-intercept that we did a moment ago crosses the x-axis, so it will have an odd multiplicity, and that's why I said it has one factor. It could be any odd power, but we're just choosing the lowest to keep our polynomial simple. We have one more 0 here. We have a 0 of 2, and our graph crosses at that point, so we're going to have an odd factor of x minus 2. So we'll keep that to the first power because the multiplicity will be odd for that 0. So when I'm forming my polynomial function, it could have a coefficient of a, which we don't know. We do know it's going to have a factor of x plus 4, a factor of x plus 2, and we're going to say it has an even number of factors because that 0 has an even multiplicity. And then we have a factor of x minus 2. Now, one other piece of information that we could glean from this is the sign of our leading coefficient. And we can figure that out based on the end behavior. So looking at the end behavior of our graph, we have both of our ends going in the same direction, and that matches with the degree that we've come up with here. So we have 2, 1, and 1, so it's a 4th degree polynomial. The ends are going in the same direction, and these ends are going both up to positive infinity. So that means that our leading coefficient will be positive. If our end behavior was going down to negative infinity, then our leading coefficient would be negative. Now I pulled this question, and the question had some multiple choice options. So I'm going to put those multiple choice options up here so that we can take a look at and see which one makes sense. So here we have a factor of x plus 4, a factor of x plus 2 squared, a factor of x minus 2, and a positive leading coefficient. So that's a possibility. So I'm going to put a question mark there as a maybe. In this next one, we have a factor of x plus 4, x plus 2, x minus 2. And this one we're going to have to rule out because this only has 3 x's. That would be x to the third power. And the n behavior wouldn't match that. In an odd power, the n's go in opposite directions. In this next one, we have x plus 4, x plus 2 squared, x minus 1. That would work. However, the leading coefficient is negative, so we know that the n behavior would be going to negative infinity. So let's rule that one out. The next one has x plus 4, x plus 2, but only one power of x plus 2, or one factor of it. So we know that doesn't match the multiplicity at that point. The next one has x plus 4, x plus 2, x minus 2. The multiplicity doesn't match, and also the degree doesn't match. That's an odd degree, and the n behavior doesn't match for an odd degree. Then we have x plus 4, x plus 2, x minus 2, but our multiplicity doesn't match on these two, so we can rule that one out. And we have only left with one option for this particular polynomial function. That's f of x equals 1/16 times x plus 4 times x plus 2 squared times x minus 2. Use the remainder theorem to find the remainder when f of x is divided by x minus 2. Then use the factor theorem to determine whether x minus 2 is a factor of f of x. We're working with the polynomial function f of x equals 4x cubed minus 13x squared plus 7x plus 10. So first we want to use the remainder theorem. The remainder theorem says that f needs to be a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. So we have this polynomial function, and we want to divide by x minus c, which is x minus 2. That means we can calculate the remainder by calculating f of c, which in our example is f of 2. So let's calculate the remainder. F of 2 is 4 times 2 cubed minus 13 times 2 squared plus 7 times 2 plus 10. That gives 4 times 2 cubed, which is 8, minus 13 times 2 squared, which is 4, plus 7 times 2, that's 14, plus 10. 4 times 8 is 32. 13 times 4 is 52. And 14 plus 10 is 24. 32 plus 24 would be 56 minus 52 gives us a remainder of 4. So the remainder of f of x when it's divided by x minus 2 is 4. So in the second part it says use the factor theorem to determine whether x minus 2 is a factor of f of x. So I have the factor theorem here. Let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c equals 0. So remember, we just divided by x minus c, and we calculated f of c to be the remainder, and if that remainder is equal to 0, then we know that x minus c is a factor. So we got f of 2 to be 4, so the remainder is equal to 4, and since that remainder is not equal to 0, that means that x minus 2 is not a factor of our polynomial 4x cubed minus 13x squared plus 7x plus 10. In this example, we want to use the rational zeros theorem to find all of the real zeros of the polynomial function. Use the zeros to factor f over the real numbers. Our polynomial function is f of x equals 2x cubed minus x squared plus 2x minus 1. So with the rational zeros theorem, it says that if our polynomial function is going to have a rational zero, it has to come from a very limited list based on our leading coefficient, which we call q, and our constant term, which is what we call p. So we're going to start off with listing the factors of these numbers. So the factors of p equal 1 are going to be plus and minus 1. The factors of q equal 2, those are going to be plus and minus 1 and also plus and minus 2. And the rational zeros have to be among the list of p over q. So what we do is we come up with all the possible combinations of these factors of p over q. So our potential rational zeros are going to start off with this 1 in the numerator. So it's plus and minus 1 in the numerator, and this plus or minus 1 in the denominator. And then we only have one other possibility for the denominator, and that is a plus and minus 2. So we have plus and minus 1 over plus and minus 2. If we reduce that, we end up with 1 over 1, which is 1. And that could be plus or minus 1. And 1 over 2, and that could be plus or minus 1/2. So we have 4 potential rational zeros. So we are going to now test out these zeros using our remainder theorem. The remainder theorem says that if we get a remainder of 0, then we have a factor of the polynomial. Well, I guess that would be the factor theorem, not the remainder theorem. So I've got my graphing calculator here. We're going to use it to help us work out this math. And in the y equals menu, I'm going to type our function 2x cubed minus x squared plus 2x minus 1. Well, I've typed that wrong. Let me try it one more time. 2x cubed minus x squared plus 2x minus 1. And I'm going to use my table. And before I use that table, I need to go to table set. I want to switch this over to ask mode so that I can specify these potential rational zeros to test out. So in my table, I'll substitute in a 1, negative 1, a 1/2, excuse me, that should be 1/2, and negative 1/2. So the remainder theorem says that if I substitute these values in here, I'm getting the remainder when I divide by the factor of x minus 1, x plus 1, x minus 1/2, x plus 1/2. If that remainder comes out to be 0, then we know we've identified a factor of the polynomial. So because this remainder came out to be 0, we've identified a factor of the polynomial to be x minus 0.5. So we've identified one zero of the polynomial, a factor of the polynomial, and we can now reduce the polynomial by that factor. So I'm going to divide x minus 1/2 out of this polynomial using synthetic division. So I'm going to put 1/2 here. The coefficients of the polynomial, 2, -1, 2, and -1. We bring down the first term and multiply by our number. So 1/2 times 2 is 1. We add these guys together to get 0. 0 times 1/2 is 0. Add these guys together to get 2. 2 times 1/2 is 1. And we get our remainder of 0 again. And now we have reduced our polynomial down to 2x squared plus 0x plus 2. And I know I can write my polynomial in factored form, x minus 1/2 times 2x squared plus 2. I can factor this polynomial a little bit more. Both of these have a 2 in common, so I can factor that 2 out. And that would leave me with x squared plus 1. And we don't really like to write these fractions in here, so I'm going to distribute this 2. And that would give me 2x minus 1 times x squared plus 1. So we've written the polynomial in its factored form, and I want to finally make sure that I've identified all of the real zeros. So let's set these factors equal to 0. So if we set 2x minus 1 times x squared plus 1 equal to 0, I would have 2x minus 1 equals 0 and x squared plus 1 equals 0. I add 1 to both sides to get 2x equals 1. Divide by 2, and that gives x equals 1/2. With the other factor, I subtract 1 on both sides. That gives x squared equals -1. Take the square root of both sides, and that gives x equals plus or minus I. So we do have one real zero of 1/2. This is the one we identified earlier. But the other zeros that we have identified here are not real zeros. These are complex zeros. So we only have one real zero of 1/2, and we have the factored form of our polynomial. Use the intermediate value theorem to show the following has a zero in the given interval. Approximate the zero correct to 2 decimal places. The polynomial function we're working with is f of x equals 3x cubed plus 9x squared minus 9x plus 9. And we want to show that it has a zero on the interval from -4 to -3. I've written out the intermediate value theorem here. Let f denote a continuous function. If a is less than b, and if f of a and f of b are of opposite signs, then f has at least one zero between a and b. So in order to prove that there is a zero on this interval from -4 to -3, we need to show that the y values at those points have opposite signs. So I'm going to use my calculator to help me show this. So I'll type into the y equals menu the function that we're working with. It's 3x cubed plus 9x squared minus 9x plus 9. And I'm going to go to the table. And right now my table is in ask mode, so I'm going to clear out these values that are here. I need to do that by deleting. I think I can go to the top of the list. No, maybe not. I just have to delete them one by one. And I'm going to type in -4 and -3. Okay, so these are the y values at these points. The y value at -4 is -3, and the y value at -3 is 36. So f at -4 is -3, and f at -3 is 36. And so you can see that f of -4 and f of -3 have opposite signs. So because f is a polynomial and is a continuous function, and we have shown that the y values have opposite signs, there must be a 0 between -4 and -3. So now we want to narrow down what that 0 is. So once again, I'm going to use my graphing calculator, and this time I'm going to use the table menu in just a little bit different way. So I'm going to go to Table Set, and this time I'm going to go in Auto mode instead of Ask. So let me switch this to Auto, and I want to start my table at -4 because that's my smaller x value. And I want my change in the table values to be 0.1. So that means that it will auto increment up by 0.1. So let's take a look at what the table looks like. All right, so let me go back and double check that I've done that right. Okay, so I have it in auto. And let's go to the table. Okay, so I've got it starting at -4.5. I want it to start at -4 and increment by 0.1. Okay, so there we go. Let me get a screenshot of this so we can take a closer look at it. So here's our screenshot. And once again, I want to use the intermediate value theorem. The intermediate value theorem says that when we have a change in the signs, we can identify that the 0 is between those two values. So we're looking at the y values here, and you see that there is a change of signs from -4 to -3.9. So I know that originally we have shown that the 0 is on the interval from -4 to -3, and now we've narrowed that down even more to say that that 0 must be between -4 and -3.9. So I want to narrow it down even more, and so what I'm going to do is change my table set once again. So if I adjust my table set, I still want the table to start at negative 0.4, but now I want my change in values to be even smaller. So I'll make it 0.01. And let's take a look at the table now. So now my table is incrementing 0.01. Let's get another screenshot of this so we can take a closer look. And once again, we want to use that intermediate value theorem to notice when there is a change in signs. So we can see here there's a change in signs in the Y menu, and that happens on these two values here. So just to recap, we originally started with the intermediate value theorem proving that there was a 0 between -4 and -3. Then we narrowed that down to be in between -4 and -3.9. And now we're narrowing it down to be in between -3.96 and -3.95. So we want to go one more iteration of this so that we can have our 0 accurate to 2 decimal places. And you can see that we already have 2 decimal places here, but we need to know what the third decimal place is to know whether we need to round to have the second decimal place a 6 or a 5. So we're going to do this process one more time. So we have our calculator again. And I'm going to have my chart over there so I know what to do the table set at. And this time I want to start at -3.96. And I want to make the change in my values even smaller, so it'll be 0.001. And let's go to the table, and once again we're looking for a change in Y values having opposite signs. So let's get a screenshot so we can look closer again. Okay, so now we can see that we have a change in signs occurring right here with these X values. And so now we're going to know what to round to. So now we've narrowed the 0 down to be in between -3.952 and -3.951. And so since the 0 is in between those two values, we know if we round to 2 decimal places, that 0 would be -3.95. List the potential rational zeros of the polynomial function. Do not attempt to find the zeros. We're trying to find the potential rational zeros of f of x equals 2x to the 4th minus 4x cubed plus x squared minus x plus 1. We're going to find these potential rational zeros using the rational zeros theorem. With the rational zeros theorem, we need to have a polynomial function which has integers as the coefficients. And the rational zeros will be in fraction form p over q. And what we see here is that p must be a factor of a naught, and a naught is our constant term, which in our example is 1. Q must be a factor of a sub n, which is our coefficient of our leading term for this function, is 2. So we can form the potential rational zeros by finding the factors of p and finding the factors of q and forming this rational expression from those factors. So let's first find out what the factors of p and q are. So p is a factor of a0, so p will be a factor of 1. The factors of 1 are plus and minus 1. And then q will be the factors of our leading term, which is 2. The factors of q are plus and minus 1 and plus and minus 2. So our potential rational zeros will be of the form p over q. And so they could be plus and minus 1 over plus and minus 1, or plus and minus 1 over plus and minus 2. We'll reduce each one of these to get plus and minus 1 and plus and minus 1/2. So the potential rational zeros for this polynomial function are positive and negative 1 and positive and negative 1/2. Thank you for checking out my videos. Have a great day.